Okay. Let's take a look at 3 and 4 now. So 3 blocks connected, pulled to the right with a tension of 65 newtons here. Determine the acceleration of the system. You don't want to draw the force diagrams for this yet. Okay, so this one, you know the masses of everything, and you know the force being applied to accelerate it. All right. These strings inside here, we're going to call this FT1 and FT2 here, right? The tension forces pulling on these blocks. We're going to do that because we're going to have to find those. But to get the acceleration of the system, we're going to think of these all added together here, right? So ultimately what we have here is a 12 plus a 24 plus a 31 kilogram block. All right, so that looks to be about 67 kilograms of mass being accelerated by a 65 Newton force. Now, it's frictionless, right? So there's no frictional force going back the other way. So the acceleration of the system is simply the net force acting on it divided by its mass. So 65 newtons trying to accelerate it, 67 kilograms. I think it gives you about 0.97 meters per second squared or so. But let me just double check that before I commit it. Yep, 0.97 meters per second squared. All right, so now to figure out the tension in each string, we're going to have to look at the force diagrams. All right, so we'll call it block 12, right? The 12 kilogram block. It's got its FG, it's got its FN, and it's got FT1 pulling it to the right. Now the middle block, it's got its FN and its FG. FT1 is pulling it to the left. FT2 is pulling to the right. That's the 24 kilogram block. Now the 31 kilogram block, right? This has its FN, its FG. It's got this applied force pulling it to the right, 65 newtons, and it's got FT2 pulling it back to the left. And each one of these blocks is accelerating to the right at 0.97 meters per second. They all have to have the same acceleration because they're all tied together and heading in the same direction. So FT1 is pretty straightforward defined, right? Because we can just look at this one block, right? We can say FT1 equals MA. All right, we know the mass of this block. So FT1's got to be 12 kilograms times 0.97 meters per second squared. 12 times 0.97 is 11.6. Now, I am going to write it with one decimal place here. I'm going to be a little bit loose with my sig figs here. I guess 65.0, that is 3 sig figs. I guess I should have made this 12.0, 24.0, and 31.0. So we'll say 11.6 newtons. Now for FT2, let's see if I can use this. So for this one, I'd have to do FT2 minus the magnitude of FT1 equals this mass. We'll call it mass 1, 2, and 3, I suppose. Times the A. All right, so A I know, FT1 I know. I can solve this for FT2. It might be an easy way to go. Let's go ahead and do that, and then we'll go over here and solve this one. So FT2 is going to equal, move this over here, it's going to be equal 24 kilograms times 0.97 meters per second squared plus 11.6 newtons. So 24 times 0.97. Interesting note here, this is the net force, right? About 23.3 newtons. This is the net force required to accelerate a 24 kilogram block at a rate of 0.97 meters per second, right? So since it's getting pulled to the left with 11.6 newtons, this force the F12 has to be 23.3 newtons bigger than the resistive force, right? Because the net force here. So it's going to be 23.3 plus 11.6. Why am I putting this in calculator? 34.9. 34.9 newtons there. All right, and then finally, let's see if it checks out with this one here. So over here now, Newton's second law is going to tell us that the applied force minus Ft2 has to equal m3 times A. So this, I'm going to do both sides of the equation here to see what, sorry about that, to see what I get. So F is given, right? That's 65.0. Ft2 is given. We calculated, sorry, 34.9. Let's see if it equals MA. MA is 31 kilograms times 0.97 meters per second squared. So 65.0 minus 34.9 is 30.1. 31 times 0.97 is 30.1. Check. Works out. So FT2, FT1, FT2. There you go. All right, I'm going to pause this video here really quick. Before I do this one, I got to see if anybody's trying to video conference with me. Oh, shook it a little bit. This one here, coefficient of kinetic friction between M2 and the horizontal surface is 0.50. All right, M2 is 2 kilograms, M1 is 4.0 kilograms. This angle is 30 degrees. Determine the acceleration of the system. Okay, so we could do the blob method here, but chances are that's going to be hard for you to identify the first time you see it. So what we're going to do here is we're going to draw force diagrams for each object, M1 and M2. All right. And then see if we can't figure out what the net force is acting. So M1 definitely has its own gravity, M1G, pulling it down. It's going to have this tension pulling it up the ramp, and it's going to have a normal force acting on it. No friction on it, right? So our coordinate system is going to look like this here, right? Inclined plane. The angle here is 30 degrees. Should have wrote this over here, I suppose. Up here on the ramp, we're going to have its Fn. We'll call this Fn1, Fn2. This is going to be M2G going down, and its force of tension is going to be pulling it that way, and we're going to have a force of friction. All right. So, if I think about this system as a whole, right? So it's total of 6.0 kilograms. What forces are acting on it to try to accelerate it? Well, these are all the forces. This is what you have to choose from. What's trying to accelerate it? Well, the normal force and gravity are definitely not trying to accelerate it, right? They're balancing each other out. Same thing over here. But you got to remember, on the angled inclined plane here, you got to break that force of gravity into an x and y component. All right, FGX, FGY. So FGY cancels at the normal force. FGX is trying to accelerate it down the ramp. The tension here, the tension is tying these two blocks together to make them one, essentially. This is essentially one 6 kilogram mass trying to get pulled down the ramp. All right? So the only force that's pulling it to the left here is the x component of gravity. If we treat this all as a system, right? The tension is simply holding the masses together. Now, what's trying to pull it to the right here? Friction. Force of friction is trying to pull it to the right. All right, so any other forces that I need to consider? Well, again, why not the tension? Well, because the tension's pulling inside of this blob, right? They're canceling each other out, essentially. Tension does not cause this whole thing to accelerate. It causes M2 to accelerate with M1. The force that's pulling all of this down the ramp is FGX. The force that's holding it back is the force of friction on 2. So, looking at this, I have to figure out what FGX is. I have to figure out what force of friction is. So, over here, FGX, right? FGX is going to be M1 is 40 times the sine of 30, because remember, it's the opposite side to get the x component. So 20 newtons is FGX. Now, force of friction, I'll get that from this force diagram. Force of friction's got to be mu times the normal force, right? Well, force of friction here is 0.50. The normal force on block 2 is about 20 newtons. Force of friction, the magnitude of it, these are just magnitudes. I haven't put signs on anything yet, right? We're going to make the left positive in this. All right, we're going to make this the positive direction, that the negative direction, because it always makes the math easier to make the direction of the acceleration the positive direction. All right, so when I write Newton's second law for the system, it's going to be FGX minus the force of friction equals mass of the system times the acceleration of the system. So FGX is 20 newtons minus 10 newtons equals 6 kilograms times A. A is 10 over 6, which is like, what is that, 1.7? 1.67? Yeah, so 1.7 meters per second squared. So this system is accelerating at a rate of 1.7 meters per second squared down the ramp. Bam. Great. Now, determine the tension in the string. All right, so I need to go look at these force diagrams here, all right? It's kind of like double arrows here. I might write it down here. So I have to make Newton's second law equations for these two force diagrams to be able to get the tension in the string. Or I can pick whatever one's easiest. Let's write Newton's second law for each one of these and then see which one's easiest. So Newton's second law here, I'm making down the ramp the positive direction. I'm making to the left the positive direction on this one. So it doesn't matter. They're both I'm making the direction of the acceleration the positive direction. So in this case here, Newton's second law for M1. So this is the x direction for M1. Right? It's going to be FGX minus the force of tension equals M1 times A. For the x direction of M2, its force of tension minus the force of friction equals M2A. I'm looking for, oh sorry, this is force of tension, not F2. I don't know why I wrote that. Whatever one of these, it doesn't matter. I can use either one of these to find the force of tension. I already calculated FGX. I already calculated force of friction up here. It really doesn't matter. So I guess I'll just use this one here. FGX was 20 newtons minus the force of tension equals 4 kilograms times 1.7 meters per second squared. And now note that this just is positive. The net force is positive because I said down the ramp was positive. Down the ramp force is gravity's x component. It's positive. The tension here I wrote as negative. So now when I solve this, I'm going to be solving for the magnitude of the force of tension. I already counted for the sign on the tension by putting it there. All right. So 4 times 1.7 is, 4 times 1.7 is about 6.8. So force of tension, I'll bring the force of tension over here, bring this over here. So the force of tension equals 20 plus 6.8. So 6.8 newtons represents the net force that is accelerating M1. 4 kilograms at 1.7 meters per second, that's 6.8 newtons. So if I know gravity pulls with 20, oops, my bad, it's minus 6.8. If I know gravity pulls with 20, right, then that must mean the tension is taken away enough of that to leave behind 6.8 newtons. All right, so 20 minus 6.8 is 13.2. Ft equals 13.2 newtons. I had to make that negative. That was a bad error. I could check it over here if I wanted to, just for redundancy. Magnitude of the force of tension. I bring the force of friction over here now. I already figured out that that is 10 newtons. So bring the force of friction over here is 10 newtons plus 2 kilograms times 1.7 meters per second squared. 2 times 1.7 is 3.4 plus 10 is Ft equals 13.4 newtons. Now, why different, right? It's all in the rounding of gravity here, right? If I had used 9.8 for G on these, so this would be 30, this would be 4 times 9.8 times the sine of 30. That would have been 19.6, not quite 20. This one here would have been 0.5 times 2 times 9.8. That would have been 9.8. The numbers would have been a bit closer here. All right, but that's good enough for what we're doing here. 13.3 to 2 sig figs, which is 9.8 anyways. You got 13 and 13, all right? That one I had done fully. This one I had started. This one gets really messy when you plug in A here. It turns into a huge mess to solve for F. It's really ugly in the end. It's almost easier if you have numbers and can simplify it a bit. The last one is this forces practice on the back here. This is a really good one. We didn't fully go over this in class today, so I might shoot another video a little later tonight if I have a minute after kids go to bed. We'll see though. I'm gonna upload this for now. A couple of you asked for this, so here you go.